and then I will share my screen. Okay. As you remember, on past lecture, had I have considered this very simple rectangular cross section, which is subjected simultaneously to an axial force N and a bending moment M, and the bending moment N M is equal to N, the axial force, times H over 6. So our cross section is rectangular one, so the width is denoted as B and the height is denoted as H. What I have requested to the students, what I requested to you, was to evaluate the stress distribution, the normal stress distribution associated to normal force N and to bending moment, and to try to compute the maximum and the minimum normal stress. Okay, the first question, and I would like to ask your voice, is: have you done this exercise? Have you tried to do this exercise? Please say yes if you have done this. So, I do not hear any yes.
Yes, but I'm not sure if I got it correct or not.
Okay, I will show you if it is correct now. So at present I've received just one yes. More yes. So at present I have more than 60 persons in the virtual room, and out of 60, just one tried to perform, to do this homework at home. Of course, as you can understand, I don't think this is a good result for the class. Okay, so let's see what happened. What I expect is that due to the presence of the axial force, I will have a uniform distribution of stresses, while due to the presence of the bending moment, I have a linear distribution of the normal stresses, with a maximum normal stress in the upper part, for example, and a minimum normal stress in the lower part. Generally, it is possible to express the combination of an axial force and a bending moment as just an axial force which is not applied corresponding to the center of our cross section, but it is applied at a certain distance from the center. This distance is denoted generally as eccentricity, and in the general case, the eccentricity is the ratio between the bending moment and the axial force. Since I expressed the bending moment as the product of the axial force times h over 6, in this case, the eccentricity is simply h over 6. So now, once I have reflected on this aspect, and so on the possibility of expressing the combination of axial force at bending moment as just an axial force with an eccentricity. Why this is important? Because if the eccentricity is quite low, we have to expect a certain behavior of the cross section. When the eccentricity tends to be large, okay, or larger, we have to expect a different behavior of the cross section. Let us clarify what I mean for a different behavior of the cross-section. Okay, due to the effect of the axial force, N, I have an uniform value of the stress. So sigma associated to axial force N is simply equal to the axial force over the area of the cross-section. On the other hand, the normal stress associated to bending moment is equal to the value of the bending moment times epsilon, and epsilon is just the distance from the sensor over the inertia moment. Of course, since the bending moment and the axial force are simultaneously applied, I have to compute the resultant stress obtained by summing up the value of the sigma n and the value of sigma m. Okay, so what I expect, for example, that corresponding to the upper border of the cross section, since I have that sigma n and sigma m as the same sign, they have to be summed up with the same sign. On the other side, I have a sigma n in compression while sigma m is in tension. So I have to subtract the two values. And so I will obtain a maximum compression corresponding to the upper border and a minimum value, I don't know if in tension or in compression, because it depends on the numerical value of sigma n and sigma m. I have the lower value on the lower border, on the bottom border of the cross section. So let's try to make the computation. Okay, n over a, but I know that a is equal to b times h. Okay, m times the upper value of epsilon. The upper value of epsilon is, of course, h over 2. The value of the bending moment is n times h over 6. Afterwards, I have to introduce sorry, just 1 over the inertia of the cross section. So 1 over b h cubed over 12. So very easily, it is possible to simplify this with this. And so I obtain basically from this value n times h over 6 times h over 2 times 1 over bh cubed over 12, simply again n over b times h. So the upper stress is 2 times n over bh. Okay, since I have understood that the value of the upper stress associated to the bending moment is equal to n over bh, I have to assume, I have to conclude that also the lower value is equal to the same. And so in the bottom border of the cross section, I have a sigma low which is equal to n over bh minus n over bh equal to 0. So very easy computation in order to remember what happens in the past, but also what happens in the near future when we have to talk about the cross section in steel. We will also see that when we will discuss the behavior of the cross section in reinforced concrete, that behavior is much different and a little bit more difficult. Okay, now I would like to ask to the only person who said yes to the previous question if her results were correct or not.
Yes, it was the
Okay,
same one.
good. I'm very glad of hearing this. Perfect. So now, after this first check, let's move again to the behavior of the cross section in steel. We have already discussed the aspect that we are seeing. So we have introduced in the elastic range normal stress associated to bending moment, normal stresses associated to axial force, shear stress, and we were discussing about what happens to a cross section under bending moment beyond the elastic range. And we have seen that in order to understand what happens, first of all, we have to assume a stress-strain relationship for the steel material. And we have assumed a linear behavior until the yielding. Afterwards, the stress does not increase no more anymore. So while the strain can exceed the value of the strain at yielding, the corresponding stress does not exceed the value at yielding. So this is a first aspect needed to understand which is the behavior of a cross section outside the or beyond the elastic range. The other important aspect to be recalled is that we assume, exactly as it happens in the elastic range, that under bending moment, our cross section rotates remaining plane. So if the cross section is every cross section in steel or in reinforced concrete rotates remaining plane, what we have to do in order to understand what happens beyond the elastic range is to increase the rotation of the cross section in order to obtain the strain profile and then use the relationship between stress and strain in order to evaluate the increase in the bending moment, of course, but also the changed behavior in the of stresses in the plastic range. First of all, of course, it is very easy, basically, to evaluate the bending moment corresponding to the yielding of the cross section, because we are, of course, still with all fibers in the elastic range. The extreme two fibers are subjected to a strain which is equal to the yielding strain, and the corresponding stress is equal to the yielding stress. So basically, we can easily define the moment at first yielding, or MY, as basically the product of the stress at yielding times BH square over 6. This value has been defined as WL. But what happens when we are dealing with a plastic behavior? Okay, so the bending moment is going to increase, and so we have that the strain profile changes. For example, we have that for a changing strain profile, that some fibers are some fibers undergo a deformation which is larger than the yielding strain, whereas generally the internal part of the cross-section is still in the elastic range. What happens, of course, that if we are below the yielding strain, we have an elastic behavior like this. So a linear behavior also in terms of stress. When the strain is larger than the yielding strain, then we have a constant value of the stress, and that constant value of the stress will be equal exactly to the yielding stress. Okay? Of course, in the limit, when the strain profile becomes horizontal, of course, this is a conceptual limit, okay? It cannot be reached exactly in the practice because it means that the strength is equal to infinity. Of course, we will obtain a very high value of the strain, but not an infinity value of the strain. So, in the limit, we have, of course, that the upper part of the cross-section is yielded, for example, in tension, while the bottom part of the cross-section is yielded in compression. And so it is possible quite easily to evaluate the so-called fully plastic moment, because the fully plastic moment, of course, is the resultant of the two forces, upper and lower force, times the distance between the two forces. The distance between the two forces, of course, is equal to half the height of the cross-section, h/2. Basically, we have to evaluate the area of this rectangle. But the area of this rectangle is the area of the half cross-section. So BH/2 times, of course, the value of the yielding stress. And so, in the end, we have BH²/4 times FYD. And so, also the fully plastic moment might be expressed as the product of a final stress times a value which is homogeneous with a length elevated at 3. So that's quantity WPL, but also WL, only depends on the geometry of the cross-section, on the geometric dimension of the cross-section. In the case of rectangular cross-section, of course, B and H. When we have an I-beam, of course, it will depend also on other quantities, other geometric quantities, such as, for example, the overall height, the height of the web, the thickness of the flanges, and so on. Of course, we can obtain a ratio between the fully plastic moment and the yielding bending moment. We can observe that this ratio is exactly equal to the ratio between WPL and WL. So it depends basically only again on the geometry of the cross-section. And in the case of a rectangular cross-section, we can observe that this value is quite high. But we can also observe from real I-beams, as you can see in the exercises I've sent to you, but also in the exercise that Dr. Ruccolo will perform in the second part of the class of today, you can easily verify that the plastic ratio in I-beams is in the order of 1.1, 1.15, 1.05 is larger than 1, of course, because the fully plastic moment is larger than the yielding moment, but it's not so large, okay? So here you can see resume, a summary of what happens to the stress strain behavior and which is the consequence at the level of the moment curvature diagram. The moment curvature diagram is very similar to an elastic, ideally plastic behavior, but we have a rounded area in this region due to the fact that we are passing from this to this through the plasticization of the central fibers of the cross-section. I have already commented about the industrial production in Europe, but I will show this with much more detail in the second part of my presentation, and I will already commented about the possibility of having different kind of cross-section like IPE or HEA and HEB and HEM. And for all this kind of profile in the standard textbook, but also in the standard manuals, we can find not only the basic geometric dimension like h, the overall height of the cross section, p, the width of the profile, the thickness of the web and the thickness of the flanges, the area and so on, but also the inertia bending moment and the geometric characteristics we have denoted, that we have called WL and WPL. And of course, we generally refer to the two main planes of behavior of the cross section, the main inertia axis, and the manuals give to us the value corresponding to this inertia bending moment and W and WL and WPL values. Okay. You remember that in the past lecture, we have also commented about the possibility of dividing a bending moment. One general bending moment, for example, in the elastic range, we can refer to the yielding bending moment in the part which is carried by the flange and in the part which is carried by the web. We have demonstrated, we have verified that, for example, if I want to evaluate the bending moment carried by the web, the part of the yielding bending moment carried by the web, this part is equal to the yielding bending moment times the ratio between the inertia moment only of the web over the overall inertia moment, okay? And similarly, I can evaluate the bending moment carried by the flange, and in this case, the bending moment carried by the flange, it's equal to my times the difference between the iota, the total value of the inertia moment minus the inertia moment of the web over the overall inertia moment. And for example, I will show you some computation. Also, Dr. Ruccolo will show you some kind of this computation in the afternoon. Antonello, we established that you will show which one?
This one, Professor.
This one? Okay. Yeah. So I briefly comment, for example, the one on the cross section HEM 340. Okay. So from the classic dimension of a profile, for example, let's go back to the HEB 340. we can remember that 340 is nothing more than the overall height of this cross section. So get a look at the dimension of the different profile, and so you will very quickly understand which is the meaning of this way of denoting the standard profile. Please note that not in every case that's equal to the height of the cross section. And we have already commented on the fact that we assume that the beam is made in steel called S235. In this class of steel, the value 235 is the yielding stress, okay? So by definition, since I have that the yielding bending moment, it's equal to the yielding stress equal to 235 megapascal times WL, what I have to do is to recover the value of WL, basically, and make this product. By making this product, it's better in order not to have a number with a large number of zeros passing from megapascal to kilonewton per square millimeter, because WL is expressed in cube millimeter, okay? If I do this, I will have, for example, 0.235 kilonewton per square millimeter times this number, and I will obtain 506.66 kilonewton per meter, okay? So I will also pass from millimeter to meter. Afterwards, I would like to evaluate the part of the yielding bending moment which is carried by the web. And in order to obtain this number, I have just to evaluate the inertia bending moment of the web. The inertia bending moment of the web, it's equal to the thickness of the web times the h of the web cube over 12. 12 is missing here, but not in the final computation, okay? Over the total inertia moment. Total inertia moment is given by the tables on the profile cross-section, okay? And so I will obtain 0.071 times 506.66 kilonewton per meter. And so I can easily see that the bending moment carried by the web is only about 7% of the entire yielding bending moment. This means that a large part of the bending moment, in this case around 93% of the yielding bending moment, is carried by the flanges, okay? This is very important in the practice, because say to us that if we are dealing with an I-beam, basically, and I want to obtain a connection between that I-beam and another kind of beam, if I want to have a connection transferring also the bending moment, I have to connect also the flanges. When the connection is only between webs, so only the web is connected, it is not possible to transfer a large part of the bending moment, and so the connection behaves like an hinge, okay? So the other aspect is passing from the elastic behavior to the fully plastic behavior. For an I-beam, it's quite easy to evaluate the value of the forces corresponding to a fully plastic cross-section. These forces basically are very easy to compute because they are equal, of course, to the yielding stress times some area. For example, if I want the resultant F1, I have to compute just the area of the flange, okay? And so if I want the bending moment, the plastic bending moment, which is carried by the flange, I have to multiply the value of this force F1 by the distance between the two forces F1. And this distance is the total height of the I-beam minus the height of the thickness or one flange. Similarly, if I want the plastic bending moment, which is carried by the web, I have just to multiply F2 by the distance between these two forces F2. Of course, in this way, it is very easy to evaluate the plastic ratio. So the ratio between the fully plastic moment and the first yielding bending moment. Of course, since we know that this coefficient is also equal to the ratio between WPL and ML, I can easily obtain that coefficient from the standard tables. For example, let's try to evaluate this value for a different profile. For example, the IPE 200 profile made again in a steel like S235. Okay, so what we have to do is multiply the value of the yielding bending moment times the area of the flange. So the width of the flange for an IP 200 is 100 millimeter. The thickness of the flange is 8.5 millimeter. So we will have a force F1 which is equal to 199.75 kilonewton. Similarly, I can evaluate the force F2 in the upper part of the web, and this force is a little bit larger than 120 kilonewton. Okay, so it is possible very easily to evaluate the bending moment which is carried by the entire cross section by summing up the bending moment which is carried by the flanges and by the web. The overall value of the bending moment is something like 49.27 kilonewton per meter. And so the value of C is equal to 1.081. So it means that according to this simplified computation, simplified because we have assumed that the cross section is made by 3 rectangles, and so by doing this, as it will be shown by Dr. Ruccolo in the second part of the lecture, we neglect the effect of this rounded part of the cross section. Okay, so but this is an acceptable approximation. What I recommend to you is to try to reflect on this kind of computation that we have summarized in this slide, because of course you will be asked to repeat this kind of computation by yourself in the first homework. And I will remember that the first homework will be used also for evaluation purposes. Okay, now I would like to understand how it is possible to verify or to check the elastic resistance of a steel cross-section. So, for example, let's assume that our cross-section is in the elastic range, okay? We will see that in some cases we are forced by the standard codes, by the Italian standard codes, by the European standard codes, to make this kind of check, so neglecting the possibility of the cross-section to underwent to a fully or a partial plasticization. So basically, we have two possibilities of working, okay? The elastic range, generally, we prefer to work in terms of stress, because if we are dealing with the cross-section of a beam, what I expect generally in a cross-section of a beam is that a general cross-section is simultaneously subjected to axial force, not axial force, to bending moment and shear. When I have to verify or to check the cross-section of a column, there is also the effect of the axial force. So if we are looking at an I-beam, and so a cross-section which is an I cross-section, and we look at one point, okay, of the cross-section, which is placed, for example, here or here, we expect that in that point there is the simultaneous action of a normal stress associated to bending moment or to axial force, and to a shear stress associated or depending on a shear action. For example, if we are effectively dealing with a beam, we will have in a beam a bending moment and a shear force. The bending moment will induce a linear distribution of the stresses, and so, for example, we will have the maximum stress at the top and bottom fiber of the cross-section. Conversely, we have seen that the shear stresses associated to shear are basically according to a distribution like this. So a parabolic distribution in the two flanges. Afterwards, I have a discontinuity in the shear stress corresponding to the passage from this larger width to the lower width of the web. And afterwards, we have an increasing nonlinear behavior with the maximum corresponding to the center of the cross-section. So it is interesting to observe that in this condition, which is basically an almost general condition for beams, what happens? Happens that I have the maximum stress corresponding to top and bottom fibers where the shear stress is equal to 0. So maximum normal stress where the shear stress is equal to 0. Conversely, we have the maximum shear stress corresponding to the center of the cross-section where the normal stress is equal to 0. But generally, we have also to consider the case here, for example, at the connection between the web and the flange. We have that position in which we have a normal stress which is quite equal, approximately equal, not so far from the maximum value of the normal stress, and also the shear stress is not so far from the maximum value of the shear stress. So when there is the simultaneous presence of normal stress and shear stress, I have to check that this formula, this resistance criterion is satisfied. So I would like to evaluate an ideal value of the normal stress, an ideal value of the stress, which is equal to square root of sigma square plus 3 times tau square. And of course, this value should not exceed the value of the yielding stress if we are dealing with what is established, what is written in the standard code. This Fy, this yielding value, will be the design value, which is specified by the standard code. Of course, when tau equals 0, we are in this position, and we have to recover also from this formula the condition for which the ideal stress should be lower than or equal to than the yielding stress, the design value of the yielding stress. When we are in this position along the center, of course, in this formula, we will have that sigma equal to 0. So square root of 3 times tau square should be less than or equal to Fy, and this means that square root of 3 times tau should be not larger than Fy, and this might be also expressed also as the fact that the maximum value of the shear stress does not exceed Fy over square root of 3. Okay, but when the shear is equal to 0, okay, and so we have just the normal stress that is associated to axial force and bending moment, we can also check the elastic, and not only the elastic, but also the plastic resistance of a steel cross section by using the so-called MN interaction domains. What is an interaction domain? Okay, first of all, let's assume that our cross section is in the elastic range. Okay, if our cross section is in the elastic range, the maximum bending moment is the bending moment at first yielding, and so it will be equal to My equal to WL times Fy. Okay, this happens when just a bending moment is acting. Now let us assume that just an axial force is acting. Okay, the maximum value of the axial force is, of course, the axial force corresponding to a situation in which all the fibers of our cross section are subjected to a normal stress equal to Fy design. Okay, so we have all fibers undergoing the same elongation, the same strain equal to the strain corresponding to yielding, and so to the same stress, which is equal to the stress corresponding to yielding. So let us assume, for example, that the shape of our cross section is a symmetric shape, okay, like an I-beam like this one, which is completely symmetric. Okay, and let us refer, for example, to the horizontal axis. Okay, let's draw an MN plane. So on the x-axis, we draw the axial force. On the vertical axis, we will draw the bending moment. So on the n-axis, we will draw the position corresponding to the maximum axial force. And so I will have plus an epsilon on the positive side of the n-axis and minus an epsilon on the negative side of the n-axis. Similarly, okay, on the m-axis, I will have plus m epsilon plus the value of the first yielding bending moment on the positive side of the axis and minus n epsilon on the negative side of this axis. Now I have 4 points on the axis. I can connect the 4 points with straight lines, and I will obtain this kind of closed figure. Okay, that closed figure again is called interaction domain. And which is the meaning of the interaction domain? How can I use the interaction domain in the practice? Okay, for example, let's assume that in our computation I have obtained for a certain cross-section a value of the axial force and the bending moment. Okay, if I denote the axial force and the bending moment coming from our computation as n and m, analytically, I just to check that n over an epsilon plus m over m epsilon does not exceed the unit value, okay? If I want to make the same check graphically, I can draw the point, for example, corresponding to the computed value of n and to the computed value of m. And I would like to check if this point lies internally to the interaction domain or it is external to the interaction domain. Of course, if it is internal or belongs to the surface of the interaction domain, I can say that that point is safe, okay? So my elastic resistance check has had a positive result. Otherwise, if that point lies outside the interaction domain, then we are in an unsafe situation, okay? But of course, if I can exceed the elastic resistance of the cross section, and of course I can exceed the elastic resistance of the cross section, because we can very easily recall that this value of the axial force cannot be exceeded. But this value of the first yielding bending moment is exceeded by, for example, the fully plastic moment. And this means that if I accept the fully plasticization of the cross section, it is possible to increase this value plus m epsilon until plus mpl. And on the opposite sides, I will have a similar increase to minus mpl. Of course, I have that the points mpl here and minus mpl here are a little bit larger than m epsilon, because we have said that, for example, for an I-beam, we have that the ratio between mpl and m epsilon is 10%. is larger than 1, but it is not so larger than 1, as it happens, for example, in the rectangular cross-section. In the rectangular cross-section, MPL is 1.5 times MY, so this value is very large. But in any case, on the M-axis, value of MPL is larger than the value on MY. So in this case, we have that the interaction domain will change shape and it becomes non-linear like this, okay? But you can see very easily that this kind of non-linearity is not so different in shape by with respect to a straight line. So generally, the codes allow to make this kind of verification by using a formula which is very similar to the previous one. In the previous one, we have had the ratio between n and ny, okay? And here we have the ratio between n and MPL, plus the ratio between m and my in the previous formula, and here we have m over MPL. The summation of these two quantity still should be less than or equal to 1, okay? Again, the meaning of the Mn plastic in the interaction domain is very similar to the previous one. If the point coming from our computation belong basically to this part, is inner to the interaction domain, now we can check positively the plastic resistance or the resistance generally. If the point lies outside the interaction domain, we are dealing with an unsafe situation. Why I have shown to you the use of an elastic interaction domain and a fully plastic interaction domain? Because depending on the behavior of the cross section, I can use a fully plastic interaction domain, or I am constrained to use the elastic MN domain. So in steel structures, there is a classification of steel cross-section, okay? And basically this classification is based on the possibility of exhibiting local buckling, okay? So basically it is possible to refer to 4 classes of cross-section. For the first 2 classes of cross-section, I can use the elastic or the fully elastic interaction domain. For the upper classes, classes 3 and class 4, I have to use just the elastic interaction domain. In fact, let's try to define the 4 classes. What I expect is that in class 1 and class 2, there is no buckling, while in class 3 and class 4, there is the possibility of buckling. In fact, in class 1, cross-section are those which can form a plastic with the rotation capacity required from plastic analysis without any reduction of the resistance. So what I'm saying is that for this kind of section, of cross-section, I can really obtain the fully plastic resistance. And so for this kind of cross-section, it's allowed to refer to fully plastic interaction domain, okay? Now let's introduce class 2. Class 2 cross-sections are those which can develop their plastic moment resistance but have limited rotation capacity because of local buckling. I will try to explain something about local buckling in 2 minutes, but let's first complete this kind of definition. So we have cross-section in class 2, which can develop their plastic moment resistance, okay? Which means that this is possible to this kind of cross-section basically to obtain the fully plastic bending moment, but there is no the possibility of having a large rotation due to the intervention of the buckling phenomenon. I would like to go back to this slide because these slides clarify what is meant by the standard code, okay? Because basically, if we refer to the moment curvature relationships, what we observe? We observe that in this kind of behavior, there is the possibility of reaching the fully plastic moment. But after we have reached the fully plastic moment, there is a capacity, a further capacity of rotation. But if there is local buckling, there is no more capacity of rotation. So for cross-section in class 1 and in class 2, I can refer to fully plastic resistance. In class 2, I can also assume that I can also develop a fully rotation capacity without any reduction of the resistance. In class 2 cross-section, there is no reduction in the resistance, but there is a limited rotation capacity, okay? Let's look at class 3 cross-section. Class 3 cross-section are those in which the stress in the extreme compression fiber of the steel member, assuming an elastic distribution of stress, can reach the yield strength, but local buckling is liable to prevent development of the plastic moment resistance. It means that there is the possibility of buckling, and so I can attain, or I can look at the development of the maximum plastic okay? Assuming an elastic distribution of stress can reach the yield strength. We are referring to the extreme compression fiber, okay? Class 4 cross-section are those in which local buckling will occur before the attainment of yield stress in one or more parts of the cross-section. So this means that when we are dealing with class 3 cross-section, I have to refer to the elastic interaction domain, and I cannot accept a bending moment which is larger than the first yielding bending moment. When the cross-section is in class 4, I have also to introduce some penalty on the elastic interaction domain. What is local buckling? You remember from mechanics of material what is local buckling? Please say yes or no. I would like just to stop sharing because I would like to know if which is the number of participants. The number of participants is more or less the same as in the beginning. So you remember what is local buckling? from mechanics of materials? So you remember or no?
For me, no.
Any others? I have a couple of no from the chat.
Me too, no.
So, okay. Of course, during the next class, I will recall more extensively. But, for example, let's assume that there is a column in a normal classroom, okay? For example, you remember that in our in presence lecture of past Friday, in the room there was a very large column. You remember? Okay, what if I'm going in the close neighborhood of that column, okay, and I will apply a small force to the column, what I expect is that there is no appreciable effect, so no large displacement corresponding to that force. But more important, what I expect, if I can measure probably a very small displacement, but that displacement will vanish after the force will end. A behavior like this, so a small perturbation will generate just a small effect, is called as a stable behavior. But there is, of course, the possibility of instability, and local buckling is a form of instability. What is instability? In general, I can say that something is unstable when a small perturbation is capable of generating a very large effect. Coming to the example of the column in the classroom, a small effect is a small force, okay? The application of a small force, for example, by pushing against the surface of the column. What is a large effect? A large effect is, for example, that our column now has an inclination of 45 degrees, okay? So very large angle, very large displacement. And after the force end, we will obtain still very large inclination and very large displacement. So a small action has determined a very large effect. That is instability, and local buckling is a form of instability. But we will begin the next lecture by recalling something about instability. Now I would like to share the video at the screen again, because I would like to finish this part of the lecture with an homework. Okay, I introduced just very few comments on this homework because I have already sent to you those slides. So you have the slides, and so you have the homework. Okay, this is a very simple structure, which is a statically determinate structure. The structure is subjected to an uniform load, an uniformly distributed load, and you can see that the height of the column is beta L, and also this action, the value of this action, QL over beta, depends basically on beta. Beta is equal to 1 plus alpha over 5. Alpha depends on the first letter of your first name, okay? So if the first name is Angelo, for example, or Anna for a lady, alpha it's equal 1, and then you will have that beta will be equal to 1.2, and so this 8 will be 1.2L, and this, the value of this load is QL over 1.2, okay? So there are different exercises for different names, okay? The second homework is referring to an I-beam cross-section. Again, we have that some part of the cross-section are equal to everybody. For example, the thickness of the web is equal to 5 millimeter. The thickness of the flange is equal to 10 millimeter. The height of the I-beam is equal to 200 millimeter, but the width of the flanges it's equal to 108 plus 10 times alpha, and alpha again depends on the first letter of your first name, okay? What I ask to you is, of course, to develop these exercises as homework, okay? But in the beginning of next class, okay, when you are entering in the class, I kindly ask to write in the chat yes or no, okay? Yes, if you have done this homework. No, if you haven't done this homework, okay? Please remember that similar homework are arriving for you in order to make the evaluation, okay? So I warmly ask to everybody to do the homework, okay? Now I would like to very briefly begin the last part of my lecture. So I'm sharing the screen. It's okay? You are seeing my screen? It's okay.
Yes, we see.
Okay, perfect. Perfect. Good. So before talking about buckling and instability, very briefly, I would like to talk you about the historical development of iron structure, the properties of cast iron, wrought iron, and beam. I will show very quickly resin structures in steel, and I will discuss also very briefly some material properties and some definition, and I will show you the commercial product. Of course, I will try to end my lecture in 15-20 minutes because I have to show you a large number of slides, but these slides are quite easy, and of course I will send all these slides to you again at the end of the class. So if we want to look back at the historical development of iron structure, there are some possibility of testifying the presence of iron structure until 2000 years ago, with some iron chain suspension bridges in China. Of course, the Greeks used lead copper clamps in their columns, but in the Middle Ages there was a large use of iron ties in masonry buildings, and I will show you some example. The beginning of the iron construction dates back to 1779 with the iron bridge at Colebrookdale, and I will show you the bridge. But of course, the golden age of iron construction is the 19th century, and also 19th century marks the beginning of steel structure. So the first example of course, the iron ties that still we can observe in our historical construction, in our historical center. Typical iron ties are in the Cathedral of Milan. Dr. Rucco knows very well this kind of structural element because on a platform he tested several of these ties, and in fact you can see here applied on a ties at an height of about 30 meters from the ground, an accelerometer used for testing this kind of structural element. Other kind of pictures of those structural elements in order to show you that those kind of elements are very far from industrial production. They were produced manually, basically. But as I have said to you, the first iron bridge dates back to 1779. You can still see this bridge in UK, and there is a picture of this bridge, some picture of the bridge with some person here, in order to have the possibility of appreciating the overall dimension of the bridge. And on the left-hand side of the slide, you can also see something from the structural drawings of the bridge. Of course, this is a very well-known bridge, the Garabit Viaduct. Maybe someone of you have seen a film of several years ago. The title of the film was Cassandra Crossing, with Sophia Loren, if I remember well, and the main actor in terms of steel construction of this film was the Garabit Viaduct, which was designed by Gustave Eiffel in 1884. And here in this slide you can see some details of the arches. But of course, the masterpiece of the age of iron construction was the Eiffel Tower, which you can still see in Paris. The Eiffel Tower was completed in 1889, and 1889 was also the year of the Expo in Paris. Okay, a very nice structure in iron that was basically built corresponding to the Expo in Paris in 1899 was the Galerie des Machines. Unfortunately, it was demolished after the completion of the Expo. But this kind of structure is very interesting because you can see something very similar in the railway station of Milan. In the railway station of Milan, we can observe at the basis of the columns some hinges which are very similar to the one that were present in the Galerie des Machines. In addition, you can see here a picture of the Gallery of the Machine after its completion, and of course you can easily understand that this is the dimension of a man, and so you can appreciate the overall dimension of the Galerie des Machines. And here you can see basically some drawings of the structure. Okay, looking at the difference between modern steel, cast iron, and wrought iron. So the cast iron is made of iron in a percentage ranging between 95 and 98%. Iron is characterized by cast iron is characterized by a high compression strength, a lower tensile strength. It is brittle. It is basically like a masonry, so the unlike masonry is characterized by a very high compression strength. The translation of cast iron in Italian for some Italian students, but also for foreign students, is ghisa. Cast iron is ghisa in Italian. Wrought iron is ferro pudellato in Italian. It's the percentage of iron is higher, and it is characterized by compression and tensile stress. It is weaker than modern steel. Modern steel has a percentage of iron which is ranging, is similar to the one of wrought iron, but the difference between steel and wrought iron is carbon and other impurities that characterize all the properties of the modern steel. So if we want to compare the stress strain curve of concrete, cast iron, and steel or mild steel, for example, we can see that concrete basically is linear or almost linear until the collapse, the maximum strength is reached. Cast iron has a behavior that is more or less similar in compression to the concrete or to masonry. Of course, the strength is much higher. In terms of mild steel, there is a linear behavior until this value, which is yielding, and afterward we have an hardening phase of the behavior of the material. And of course, the value of the yielding stress, but also the value of the maximum stress is much higher than cast iron. So I will show you very, very quickly some example of recent structure. For example, this kind of footbridge in which you can see that the hand of the architecture is very well seen. This kind of footbridge, I have shown some pictures and some drawing on this footbridge during my first class. This is in Italy, very close to Cortina d'Ampezzo. Other kind of different footbridge in Spain. There are 4 footbridges in golf course in Spain, and this structure dates back to 2005. And for example, we can see that this kind of structures are quite light, and so it is possible to make a transportation of a structure like this in 2 or 3 pieces from the fabric, from the industry, and afterward we can structure in some water tanks. Okay, this is another what happens. Che cosa succede? Proviamo a uscire. Mi vede adesso? Tonello?
Sì.
Okay, so you can hear me?
Yes, Professor, we just
We
lost
just-
you for a minute.
Yes, you have lost something. What we have lost? This one, have you seen this one?
Yes.
Okay, so you have also see this one.
Yes.
Okay, this one.
We were where there was the they were lifting the structures.
Okay, so the last slide you have seen is this one. Okay,
Yes.
perfect. So I have just introduced this one, in which there is again a suspension bridge in Italy, in Casalecchio di Reno, near Bologna, and this I have just commented that this kind of bridge is a very interesting architectural design, and there is also a similar bridge more closer to Milano, in Parco del Serio, near to Seriate, about 50 kilometers far from Milan. You can see that there is that the two bridges are similar, but the difference is that the design, the structural design of this first footbridge is very sound, and so there are no issue about comfort and vibration of this kind of footbridge. In this second case, we have measured with our laboratory a very high acceleration in the order of 0.5 g, okay? So 5 meter per square second. Other kind of more engineered structure, so this kind of bridges in the close neighborhood of Milan, which was open corresponding to the Expo 2015 in Milan. Other different structure, for example, in Germany, this is a view towers in a town park, and the interesting aspect is that you can see some detail that this tower was entirely funded by the people in Germany, in Hamburg. Okay, so every person interested funded one piece of the stair, and after purchasing pieces of the stair, the entire structure was funded. So you can see the stair giving rise to the raised funding for this tower, which is known as Killersberg Tower in Germany. It was built about 20 years ago, and you can easily find the history of this view tower in the web. Another kind of similar steel structure that is a railway station still in German. Both the previous structure and this one were designed by Jörg Schleich, who passed away a few weeks ago. It was one of the founder of the international studio called Schleich, Bergman and Partner. Okay, and so you can see some interesting pictures of this railway station, and you can imagine, of course, that this span is a very large span, and you can also see that here in the central part of this structure there is a truss structure passing from outside to the inside, and the reason is not only an architectural reason, but it is also a structural reason, because the static scheme of this structure is an arch with 3 hinges, like in the Galerie des Machines, like the one that I delivered you as homework, and like the one that Dr. Ruccolo showed you in the second part of this of this lecture of today. And in this part, there are the fiber in tension. So there is a strengthening by using a truss girder in this part where the fiber in tension are the inner one, and in this other part where the fiber in tension are the outer one. So this is a typical example in which there is a clear superposition between architectural objective and engineering objective. Okay, you can see here some details from the structure. Another reason structure with cable. This is a footbridge again designed by Schleich, Bergman and Partners. This is a structure in France, if I remember well. This is a sport hall in UK, and again now the facade of the structure of this sport hall is entirely supported by an external series of supporting steel frames. Other proposal, this one was not really built, but it is a very interesting architect proposal, the Stretford Station in UK. Some very large building, high building in Germany, for example. But you have seen that in the last 20 years, there is a very significant rush for building very high rise buildings. Super high rise building whose height is ranging to several hundred of meters, and there is also a couple of buildings in construction whose height is around 1 kilometer. Other building, but like again make some comment about steel is a good structural material. And steel is a good structural material because it is a material characterized by very high strength, but it is also a ductile material. Ductility means that the material has the possibility of undergoing very high strain beyond the elastic range, but without losing, for example, yield strain. Okay. In addition, we can see from this curve for mild steel that the stress might increase as we increase the strain or deformation. Okay, so the ductility is very important because ductility means large displacement before collapse. And so it is opposite to brittle material which fails suddenly, like reinforced concrete, or not reinforced, like the material concrete or the masonry under compression. And there is a dissipation as steel yields, okay? And this is very important, for example, for resisting earthquakes and other overloading. Basically, the performance of steel in terms of strength, plastic deformability, and ductility, ultimate stress and ultimate strain, hardness, resistance to corrosion, and welding capacity are basically determined by its chemical composition. Because basically steel might be defined as a league between iron and carbon that can be forged or rolled when red hot. Okay, but we have also to consider that since the material is forged or rolled when red hot, also in the industrial production there is the possibility of having some geometrical imperfection, so some deviation from the expected or designed geometrical characteristics. And basically there are three types of geometrical imperfection. So the imperfection of the cross-section, which is some small deviation of the cross-section with respect to the ideal geometrical shape. Of course, this kind of imperfection are possible, but there is a very close to zero tolerance for this kind of imperfection. Okay, another kind of imperfection is a longitudinal imperfection, and we will see that the longitudinal imperfection is very important in the plastics because basically it affects the possibility of local buckling. Okay, in fact, if we have an imperfection like this or like this implies that when apply an axial load, a bending moment arises, and so the bending moment increases the value of the transversal deflection. If no imperfection are present when we apply an axial load, there is no transversal deflection and so no increase in bending moment. So basically, we can see that the imperfections are imperfections, geometrical imperfections at the level of the cross-section. Okay, geometrical imperfection of a beam or of a column, so geometrical imperfection at the level of structural element. But summing up all this kind of imperfection and also adding some imperfection due to the construction process, we can have imperfection, overall imperfection of the structural system. Of course, the imperfection at the level of the cross-section or at the level of the structural system are very low because they are checked in the industrial production. The imperfection of the structural system might be checked during construction. Okay, generally, when we are dealing with material properties, basically, we obtain the material property of a steel in simple tension tests. Okay, and generally the the sample sorry, my voice is not the one of 10 years ago. I see this. So we have a sample which is a cylindrical one, and afterwards there are two cylindrical enlargement in order to have the possibility of putting this kind of sample in the machine for the test. So if we measure the applied force and also the deformation of the central part of this sample, we can obtain some curves like this. As I have already said in previous lecture, generally we measure force and deflection, but we can transform forces in stress by dividing the force by the area of the cross-section and the deflection or the deformation, the elongation in strain by dividing the original length. And so we have a curve like this. Okay, so we have a first part of the curve in which the behavior is linear elastic. So we have linearity of the behavior, and the behavior is also reversible. So if I go from O to P according to this curve, it is possible to move back according to the same part, to the same curve. Afterwards, I have a PE behavior. PE is non-linear elastic behavior. Non-linear because the curve now is non-linear. It is elastic, so it is possible from P to E and from E to P moving up and down along the same curve. Afterwards, after the point E, a non-elastic behavior begins. Okay, so it is possible to go from E until S, but if I want to unload my sample, what happens is that the curve is different from ES, will be parallel to OP. Afterward, we have the point S. S is the yielding point. The material changes its inner properties corresponding to yielding. After yielding, of course, there is the so-called hardening, increasing, and softening part of the curve. After point E, when there is an unloading, the unloading is inelastic, and so it happens in a parallel way to the straight line OP. So when I am in S prime, for example, and I unload my sample, I will obtain a decrease of stress and strain along a curve, a straight line, which is parallel to OP. Okay, I would like to students just a quarter of stop in order to allow Antonello Ruccolo to his exercise, because the 3-inch arch is important, and it is also important to recover some concept, to recall some computational concept coming from the cross section. So before stopping, I would like that if there are some questions from the audience. Questions?
Professor, I have a question.
Yes, please.
About the superiority of steel among other materials. For example, like concrete, you were saying some features of the steel, but yeah, like ductility and high strength. But in bachelor, they taught us that there is no matter of which material, for example, between concrete or steel you are choosing. The dimensions and the calculations is the more important part of designing a structure for a building or something like that. For example, one column made of concrete with correct dimensions have the same strength of the same color made of steel, but in different dimensions. It's all about dimensions.
Yes, it is basically true. It is basically true. But what you are observing at present, it is quite slowly now reinforced concrete. It's a very interesting material, but it is used basically in normal building. If you want to build an high-rise building, a super high-rise building, generally you cannot use concrete, but you have to use steel, because otherwise the dimensions are too much. So, of course, it is true that the material is not important, but you have also to understand that the dimension of the material are very important. If you want to design something which is quite light with quite low dimension, you have to use steel or not timber, the one that it is called legno lamellare in Italian, okay? So modern timber, modern wood, okay? For example, in bridges, now in Italy, we use more or less steel. The concrete is used just for the roadway, okay, for the slab, but not for the main beam. in addition, also in order to have a brilliant earthquake behavior, this is much easy to obtain for steel construction because I have just to avoid buckling than for steel structure, because in order to obtain a very good behavior for steel structure, I have to use some very very significant details. Okay, so basically what you have said is correct, but at present what I see is that there is a move from reinforced concrete versus steel and versus wood in modern architecture. So reinforced concrete is very good for normal construction. When you want to build something special, say, from architectural standpoint, also from architectural standpoint, or from engineering standpoint, generally you move to steel. Okay, I
Thanks.
have answered to your question.
Thanks. I
Okay.
understand completely. Thanks.
Some other questions? Okay, so let's stop sharing. Let's also pause or stop the record.